Okay, yes, thank you very much. It's really a pleasure to be here at this nice meeting. And I should extend the same excuse as the speaker before. I'm doing Monge Ampere, but it is an inverse problem, and in that sense, I guess it is related to the topic of this meeting. And so what I'm going to show is joint work with Xiaobing Feng from the University of Tennessee. And if you like, I can just about see it. I actually made the slides available. So if you want to have a look at the slide, you can go to this address and look at this also during the talk now. You could also have a look at the preprint as well. Okay, so what I'm going to talk about Monge Ampere, but I mean, we have had a great introduction now to understand what this operator is about. Now, we want to find a numerical solution for it, but and actually in order to do that, we take a detour. So we look at these Bellman problems which come from optimal control. And the reason, I will explain that, but the reason why we want to do it is because somehow our philosophy was that sometimes if you want to address the problems arising from your setting, you are better off trying to solve these problems on the level of the PDEs and then discretize instead of first discretizing and then dealing with the problems. So this is really the explanation of it. And at that point, I will move to these semi-Lagrangian schemes, and they in some sense are an example of this approach. So if you don't like these semi-Lagrangian schemes or you don't know about them, you could use a different method as well and still use this relationship between the Bellman and the Monge Ampere formulation. So I'm going to introduce them, show them how they apply in this setting, and I also will finish with some numerical experiments. Okay, so first part, Monge Ampere operator, and I think this slide here, I almost don't need to put it on anymore because thank you. So that's the model problem of optimal transport. So we have, again, here we have our picture of some valleys and some hills, and we would like to move the soil across. And if we now use this quadratic cost function, as was mentioned also in the questions, then you have this Monge Ampere equation where you actually solve for the potential of the transport plan. And the feature of interest is here that you have got this determinant term and you want to understand how to best discretize it actually. So that's our aim here. To connect it, besides the seismic model we just saw now, another inverse problem I want to also explain is the inverse reflector problem. So we have, here we have got a light source. This light source is actually not represented as just purely a point light source, but as a sphere. And so there's light leaving from this point, going through the sphere. We measure sort of the intensity then here on the surface of the sphere to understand the directional features of this object. It will then, this light will hit an unknown reflector and reach then this target screen. And so we know how the light leaves the light source by looking at the sphere, how light passes through the sphere. We also know the illumination pattern on this target screen. And what we would like to compute is the geometry of this reflector here. Yes, this is also a classical problem. And without going into too many details, you still see the structure of a Monge Ampere equation. So you've got here this leading term, which is the determinant of the Hessian, and some lower order terms, which depend here on the solution U as well, on this potential. I think you can also actually still see the relationship to the transport, because we have a certain, if you think of a blob here, or if you think of a small square here, there's a certain amount of light passing through it. That amount is then transported via the reflector onto that screen. And actually, if you follow the equations, you will see that in some sense there's an optimality in there. And that's bringing in this optimal transport problem again. Now, this function f here is terrible and it involves a lot of scalar products which come from the geometric description of this reflector here. So this is the full problem, if you like. And now I have to make the omission that I look at the simplifications. And so the full problem is at the moment work in progress between me and Xiaobing, but we have already completed the work on the so-called simple Monge Ampere equation. And the simple Monge Ampere equation is already of interest because it includes a lot of the numerical challenges which come from this problem. Yeah? So the simple Monge Ampere equation is, let's say, simpler in two aspects compared to what I just showed before. The first one is that we only care really about here this leading term, the determinant of the Hessian, while we assume that the lower order terms are given. And the second aspect is that we assume we have got Dirichlet boundary conditions, while you usually would, in the optimal transport setting, look at the so-called transport boundary conditions which have a non-local characteristic. Okay, so in this talk, I'm going to focus here on this setting. But as I said, it's already of interest and poses interesting numerical questions because we have here really 4 different aspects to consider. So if you like, we want to do numerical analysis trying to understand the combination of a fully nonlinear problem, which is degenerate elliptic. So this degeneracy of the Monge Ampere operator occurs if the right-hand side f vanishes. Then you have a degenerate diffusion characteristic. It's also anisotropic, and it's something which now I happen to call conditionally elliptic. I don't know if that's an official term, but what I mean by that is that we have the ellipticity not on the whole function space, but we only have it on a subspace, so in a subset. So in this case, it's on the cone of the convex functions, but we don't have ellipticity in general. So the main feature, so you always ask, so what is sort of the engine of your problem? What is sort of driving, what is your analysis? And it is the ellipticity. The notion of ellipticity we are using here is based on a monotonicity concept. So it's not based on a topological concept, like you see very often with semi-linear equations, but it's using monotonicity. In fact, we say that a differential operator f, so we plug in here our derivatives and so on, is elliptic for us if in the position where we like to put in our Hessian, if we have here a monotonicity. So if we take here our dummy Hessian x and we take our dummy Hessian y, so that y minus x is positive semi-definite, so that's saying that y is in some sense larger than x, then f of x is less than f of y. So you have a monotonicity here in the Hessian. And so I mentioned that we have got this kind of conditional ellipticity in the sense that for the problem we consider now, so if you look at the differential operator of the simple Monge Ampere equation, we only get this ellipticity if our x and y are semi-definite themselves. So not just the difference, but also x and y themselves have to be semi-definite. Now that means your Hessians are semi-definite, so that means you're describing convex functions. And in that sense, we have the ellipticity only restricted to the set of convex functions. Now this has a problem because basically once you leave that set of convex functions, you're in a mess. And in fact what Xiaobing did with his co-workers in a review paper, they took a very simple-minded finite difference approximation and they just tried to solve the Monge Ampere equation on a mesh with 4 degrees of freedom, and they got here these 2 to the 4 solutions because basically at each node the numerical solution could either say I'm doing the correct thing and look a little more convex, or it could say do the incorrect thing and flip to something which looks concave. Yeah, you could, and actually in 2D you can see that if U is the solution, then minus U is the solution as well, because you somehow multiply eigenvalues and the product of 2 negative numbers is something positive again. Yeah, so somehow this means that there's a uniqueness issue, and that has to do with the fact that ellipticity is only there on a smaller set. In order to address this problem is really, I mean, the monotonicity is the thing which is somehow our foundation. And already before in the previous talk we had this definition of viscosity solutions. That's a way of giving a generalized notion of solution, which is based on this ordering concept of viscosity solution. So if you're familiar with the weak solutions, you know the weak solution is basically trying to play on the topological properties of your PDE. And here now we are playing upon the ordering properties of the PDE. Yeah, and the idea is now this leads to this concept of additive testing instead of multiplicative testing, which says if you've got 2 functions and we look at the difference and look at the point where this difference here takes an extremum, then we actually know that here the blue function and the this whatever it is, I think violet maybe function, they have got the same gradient at this point, and you can also order again here our Hessians. Yeah, so now we say, okay, one of them, let's say the blue one is our solution U, and psi is a test function. Then this gives me the opportunity to express the gradient of U in terms of the gradient of psi, and let's say in an inequality-like way to describe somehow the Hessian of U in terms of the Hessian of psi. And this inequality somehow now plays together with this ellipticity notion. Yeah, so I can now define these viscosity solutions for the Monge Ampere equations, where I say I now have my U. This is only maybe considered to be, let's say, continuous or even semi-continuous. And I say it's a subsolution if I now look where U minus psi, when it takes the local maximum, if at such a point I plug in now my psi into the operator and I get, if you like, the correct sign of the equation. And I do this with all possible psi's. And in fact, in reverse, I also say where I've got a local minimum, I want to produce the other sign. Yeah, so that's more consistent with the definition. And it turns out to be a very good concept to describe the solutions, in fact, in a well-posed way. But now we have Monge Ampere, and Monge Ampere is this plane of the convex function. So what we actually have to put into the definition here is we have to say right from the start that U has to be convex, because otherwise we are not where we do have ellipticity, where we don't have the monotonicity. And also all my test functions have to be convex as well. So that's somewhat important. And but if I define it in this way, and I also say that sub and super solutions give me viscosity solutions, then it's a well-posed problem. So you can say if omega is strictly convex and I've got a non-negative f, there exists a unique viscosity solution to the problem. Okay. Now we can see, so let's say if you wanted to approach this problem really head-on, there are all kinds of issues arising. So one of them, just to mention this, comes from the fact that convexity is a much less nice property when you want to look at this on the discrete level. So if you, for example, took all the convex finite element functions, they are not dense in the set of convex functions. Yeah? So you have to think of some kind of discrete notion of convexity. But then, so you have then a space of discretely convex functions, but do you also have an appropriate definition of ellipticity on precisely that space, for example? Yeah, so that would be the kind of question you have to answer if you now discretize right now at this point how I describe the problem for you right now. But we feel more comfortable with PDEs somehow, so we thought, okay, let's go on, do a bit more PDE work, and then discretize later. Okay, so that summarizes part one, and let me just put it together. So the equation we look at is the simple Monge Ampere equation, which has here the structure, which is elliptic and well-posed on the set of convex functions. Our solution concept is that of viscosity solutions, which is a meaningful concept on the set of continuous functions. The idea is to look at the extrema between U and some test function. And we see already that if you do a straightforward discretization, issues like the notion of discrete convexity raises questions. So what we do now is we rewrite the problem. Yeah? So we now look at a different class of fully nonlinear equations, and this class are the so-called Hamilton-Jacobi-Bellman equations, and they come from optimal control theory. And they have their own, let's say, well-established field with a range of numerical methods. And we want to somehow draw upon that knowledge. So how do these equations look? Just from the formal structure, so we have now a Hamiltonian H, and we just solve H of U is equal to 0. And H here looks as follows. So the typical structure is that we have now a family of these operators here. They are linear operators, and they are of second order, and they are in non-divergence form. And this family here lives under the supremum. Yeah? So you see alpha is my index to denote different coefficients here, and then the supremum is taken here over my parameterization alpha. So A is the set of the controls. And this is here the structure you tend to always get if you formulate your optimal control problem in terms of the so-called dynamic programming principles. So that's something arising there. Now, what's the connection? Well, there's a result by Krylov from the 80s. And in fact, what happened is, so historically, you should actually see that people try to understand a generalized notion of the Monge Ampere problem. They already understood a bit better the Bellman problems, and so Krylov was interested in trying to describe the one problem by the other. So at least for classical solutions, he had a result, and it said the following. So if you choose your Hamiltonian to be this guy here, so what does this mean? We have here B, you can see arises here, so our control set are now the coefficients for the diffusion. And here this A stands in for our Hessian. And so we take the coefficient as our control for the Hessian. And this coefficient then it reappears down there, so the determinant is still in the problem, but we somehow shifted our determinant into a coefficient now. So it's not a nonlinearity anymore of that type. And this whole thing here sits under the supremum as we wanted. And these coefficients, they live in this set S1. So S1, well, what is that? We have the set of the symmetric matrices, and then S1 are those symmetric matrices which have trace 1 and are positive semi-definite. Yeah, positive semi-definite is important because that means we have here degenerate elliptic problem now at this point. We have ellipticity. Yeah, and we have also this Monge Ampère operator, so that should look familiar to you. That's the thing I described before. And so what is really nice about this, what Krylov found, is the following result. So A is now just the matrix in Rn cross n. And he said, well, the Hamiltonian is 0 if and only if we have found a Hessian A here, so that you solve your Monge Ampère operator at that point, but also this Hessian has to be semi-definite. So what this means is that solving this constraint of convexity is now built into the Hamiltonian. So solving the Hamiltonian equation is equivalent to solving the Monge Ampère equation and enforcing the convexity. So what this means is if we, for example, now have a generalized notion of solution of the Hamiltonian equation, of the Bellman equation, we have a generalized notion of convexity as well. And we don't have to worry about this as a separate problem anymore. It's now part of our PDE. So that somehow was the starting point where we said, well, that actually looks interesting and seems to resolve the problem somewhat. And in fact, the idea, so graphically, you can actually display what happens. So it seems to be magic at first, and then you draw a picture and realize it's actually not such a, it's a very clear idea. So if you, to draw the picture, we have to, of course, go back to 2D. So I want to now look to have a drawing at the 2 by 2 matrices, and I look at the diagonal matrices where we have got here the parameters A and B. Yeah, so I've got here vertically, I've got here my A-axis, and I've got here my B-axis. And I now locally solve my Monge Ampère and Bellman equation with the right-hand side f equals to 1. Then, which Hessian solved this problem? Well, you can see here in FAT, I've plotted my 0 level set, and that's basically where my Hessians have to live, right? And you can see that I've got one branch here with the Bellman problem in the first quadrant. So this corresponds to the positive definite case. But I've got 2 branches for the original Monge Ampère operator. So this one here is basically enforcing if you have got Hessians here, which live here in this 0 level set, you have got something convex. If they live down here, they are concave, and if you're really unlucky with the original Monge Ampère equation, you jump between the two and you create a lot of solutions this way by combining these 2 branches. Now what Krylov thought, okay, I'm only interested in this branch, and it's actually just this geometric curve I tried to describe with my PDE. So I just removed this thing down here, and I want to have ellipticity. So in a monotone way, I just extend out of my first quadrant into the whole space. Yeah, you see also, if you look at the level sets, they monotonically extend. Yeah. So, and I think that's really, it's a nice idea. It's actually, I think, also an intuitive idea. So that's we really like that. And so now with this, you actually can hope for uniqueness on the whole space without any conditions. In fact, we can now have a new definition of viscosity solutions, which is identical to the one before, except that I deleted all the words of convexity. So that's because it's not our PDE is doing that. I don't need to explicitly enforce that anymore. Yeah, so we have got a similar definition, but it's not an identical definition. But it also means that our set of test functions now became much larger because we now also admit non-convex test functions. Okay, so then what we proved is we extended then the classical result by Krylov to viscosity solutions. So we said that this set of continuous functions which are convex and solve the Monge Ampère problem in the viscosity sense is equal to the set of continuous functions which solve the Bellman problem in the viscosity sense. Yeah, and so of course we could base it to a good extent on Krylov's original results, but I mean 2 things one had to address was now we have got 2 different sets of test functions here, so we at some point move to a larger set of test functions, and we still have to control what they do. And the other thing is that somehow the signs you can get negative signs here on the right hand side when you do your testing procedure, and the Monge Ampere operator is a bit behaving a bit weird when you've got negative right hand sides. Yes? I do, yes, if they are, yes, up to limit. No, it's not a linear analysis at all. It's, so we don't linearize anything, if that's what you mean. So, yeah, well, so you didn't say anything about proof, but proof should be easy, right? Well, let's say this proof here will be easy for Krylov. It will not be. It will be less easy for me. Oh, this one here, because so there are different things which you need to do for your Monge Ampere equation to be well posed. And there are different settings in which you can do it. So I could either say my domain is strictly convex, but have basically no conditions on my boundary data. Or there are some results, but they are more technical. You can actually, in some cases, have non-convex domains, but then you have to pose very careful conditions on your boundary data. Yeah. Well, we have this condition, and I don't know if we need it in this proof in particular. Maybe that for this particular proof we don't need it, yeah. But we certainly need it elsewhere, yes, in the paper. Yeah, but it would be a valid point to check that. I agree with it, yeah. Okay, so so this brings us now, of course, at this point here, I've not spoken about the boundary conditions. But the boundary conditions, they are actually a headache. Also, actually, for the numerical analysis, they are a headache. But before we come to that, at least I have to explain that there's also a choice there. So there are basically two ways. For this kind of equations, the Bellman type or the Monge Ampere, well, firstly, the Bellman type, I should say, two ways you might want to pose your boundary conditions. And they're both equally valid. You've got the classical way. Okay, that's easy peasy. We just say we have continuous functions, we have got values on the boundary, and we just say these values should be equal in the pointwise sense to our boundary data. There's another way of doing that, and this is the viscosity way of doing things. So what you do is you say, well, you have in the interior of your domain, you have your Hamiltonian. On the boundary, you have your boundary operator, which is just this difference. You put them both together, then you get a new operator, which people tend to call G very often. And then if you look at if you make this semi-continuous, the mechanism of the testing procedure still works through all the analysis, sort of the inequalities play out in the right sense. And you could make a notion of viscosity boundary conditions in this way. And in fact, they say slightly different things. And if you think of optimal control, in the one case, with the classical, you say, when your particle you're controlling hits the boundary, it's stuck there. The game ends for that particle, and it has to pay the cost of being at this position now. And if you say you impose viscosity boundary conditions, you might move to the boundary. Particle is not the boundary, and it can decide. Will it accept the cost of being at the boundary, or will it try to re-enter the game, go into the domain? So there's a choice. And that choice means that your PDE operator remains, so if you have lives also on boundary points. Your PDE, so you have to actually discretize your PDE on the boundary as well, in some sense. But you run out of space with your discretization. So this choice is something I mentioned here already because we are talking about how we pose our PDE, but it will be re-arise when we talk about numerical schemes as well. Okay, then we have a comparison principle. Comparison principles are very fundamental building blocks of this theory of viscosity solutions. And you can see, so we say we've got a sub-solution and a super-solution, and the sub-solution lies below the super-solution on the boundary, then our U lies below the V, sub-solution lies below the super-solution, also in the interior. And you can see maybe here already, we pose here, in fact, this is again in a pointwise sense, so you give an indication of what kind of boundary condition we think is the right choice for this problem. Okay, but we have now this comparison principle, and with that we have somehow also now described the PDE setting of the Bellman problem. Yeah, so instead we now want to look at this guy here instead of our Monge-Ampère operator because it's elliptic and well posed on the whole space. And we still keep the same Monge-Ampère solutions. And there is the question of the boundary conditions. If we need to deal with the fact that the PDE might be switched on the boundary, or if we can avoid this question. Okay, so that was, if you like, the PDE part of the talk. So now we want to discretize. But I think I should say that right now I'm going to tell you what these semi-Lagrangian schemes are. But if you have your own favorite method for these problems, you could now just take that and still solve your Monge Ampere problem if you have got a reasonable Bellman solver. Yeah, and you use your own solver. So some of these two talks are independent, the messages, if you like. But so what are semi-Lagrangian schemes? And so for me, they're a little bit the DG scheme of the fully nonlinear world, in the sense that you hear sometimes people saying DG is the second best method for the really wide range of problems. And I think you could my feeling is a little bit semi-Lagrangian schemes are the second best scheme for a fairly large problem, a class of problems where you look at problems which are fully nonlinear and in non-divergence form. But of course, having something which broadly works means there's a good community there, and I think this makes them successful. In the way also DG schemes are successful. So they are not as nice as you hope they are, so I should explain why they are not as nice. So I think there are two theorems we have to be aware of. The first one is, do we want to have monotonicity in our method? And the thing is, if you do a finite element method for a semi-linear problem, which is elliptic, you probably want to have coercivity, because you say that's really the important structure of my PDE. Now the important structure of our PDE here is the monotonicity. Yeah, so somehow, it actually is what selects the correct solution, so our numerical method should have an awareness of monotonicity. And because of that, I would say this is a theorem we actually saw already in the previous talk. You have got this theorem of Bals and Tsouganidis, which somewhat takes this on board, and it says, well, if you've got a monotone scheme and it's pointwise consistent and stable in L infinity, then your numerical scheme is converging to the unique solution of the problem. Okay, so now the problem for us was that actually Bals-Tsouganidis says, and I should highlight this here already, you want to be pointwise consistent on the closure of omega in the viscosity sense. So what Bals and Tsouganidis are saying is, we, in the original form, insist on imposing the boundary conditions in the viscosity sense. So we insist on being allowed to switch on the PDE on the boundary. Another point about Bals and Tsouganidis is also a well-posedness proof. So if you think you can apply this proof and need less than the well-posedness papers need, you probably did a mistake. So it's also proof of well-posedness of the PDE as well, in some sense. So now we have sort of committed to monotonicity. So far you don't know why the methods are not as nice as they look, but then you read about Vazov and Motzkin, which is an amazing paper because it already was written in 1952. And it says if you want to discretize a second-order elliptic PDE, and it's anisotropic in a weird direction, without specifying too much what that means, and you want that your scheme is monotone and pointwise consistent, then your stencils have to grow unboundedly. So if you think of finite difference method, you will have a huge stencil and you can't do anything about it. I mean, even if you solve a linear constant coefficient PDE, there doesn't exist any scheme which is monotone and pointwise consistent, which doesn't have a stencil which explodes in size. Yeah? And so right now, we already know that my stencils are going to explode in size as well. Like the ones that in the previous talk, the Obermann scheme does the same. Okay, so what does semi-Lagrangian do? So semi-Lagrangian is actually also similar to what we saw with Obermann's scheme. The idea is that the central differences, second-order central differences, are very nice discretizations, and they are monotone. So if you have got, focusing just on the linear term now, if you've got this linear term here, what we do is, if you want to have central differences, we just do an eigenvalue decomposition of our coefficient here. So the lambdas are my eigenvalues, the e's are the eigenvectors. And then if I take this coefficient, now use my eigenvalue expansion, then I see that in reality, these are a lot of partial derivatives in the direction of the eigenvalues, which are not mixed. So that's what the eigenvalue decomposition does, right? It diagonalizes, it gets rid of the mixed derivatives, and then I use a central difference scheme for that. That's great, but the problem is now, if you do that, then your scheme is, for a start, is not hitting any mesh points anymore, right? Because now you do a central difference discretization in a direction which is given by a coefficient. It's nothing you can choose, and it will just go in that direction. And okay, we have to think now how wide our stencil is, but where it will come down, you cannot assume to have a node. So that means you're taking, actually, if you implement it as a matrix, let's take this guy here, right? It would actually, you would have in this row of your matrix discretization, you would have an entry here, and entry here. Yeah, it's sort of smooth, smearing out a little bit your stencil, and that's artificial diffusion you're effectively introducing. And this diffusion is, of course, inconsistency. So to get rid of this, you need to make your stencil larger and larger and larger and larger. And that's somehow then, that is your way of becoming consistent again with what Vasov-Motzkin demands from you. Yeah, so what we need again is that this k is the diameter of the stencil, h is the mesh size, that k over h goes to infinity as I refine. Otherwise, we'll not get the consistency in the limit. But I have avoided the mixed derivatives. Okay, so that's summary of part 3. So we learned about the Balzerganides. I already mentioned there's a problem here with the boundary conditions again, and that Vasov-Motzkin says, unfortunately, we have to have large stencils at this point. And I also showed you discretization. Okay, so now everything is set, so we can discretize now our Monge Ampere operator with the things I showed you before. So the first step is actually really easy. We already know how to discretize this term here, so it now just lives under the supremum. So maybe as a cleanup exercise, we now want to have a better way of parameterizing our set. So what you normally do is you choose here an angle of your eigenvector, and then the length of the first, at least in 2D, of the first eigenvalue, and then because you've got trace 1, you already know what this length here is. And so that gives you supremum over the angle and the length of the eigenvectors. And here, of course, the determinant is then just the product of the eigenvectors, right? So the difficult part was actually already in the terms of formulation to just do here this linear term. And but yeah, so now where do we do it? We sort of put the stencil onto a finite element, P1 finite element space, so we allow unstructured meshes. And on the boundary itself, we just do now nodal interpolation. But the problem is, as we approach the boundary, because we now have these huge stencils, we run out of space. So in fact, then we have to shrink our stencil again. And that means if we shrink our stencil, this is not a consistent stencil anymore, right? But Vasov-Motzkin says, I made my stencil too small, so it's not consistent anymore. So there's a problem in the convergence analysis resulting from that. Okay. Now, good, but I mean, starting with some good news. Well, I think we have actually only good news. It all comes together in the end. But the very nice first good news is, so with when you go to the Bellman formulation, okay, I think you do gain that you get rid of this conditional ellipticity, but there are some other nice things you gain from Bellman as well. One thing which Bellman tends to give you is a globally converging Newton method if your discretization is monotone. Yeah, so that is something we got out as well. So we have a semi-smooth Newton method for our problem, and it shows us the well-postness of the finite dimensional equations as well. Yeah, and this is actually a very old algorithm. It's also in the semi-smooth Newtonness, if you like, is the new fashionable name, but in fact the Bellman people call this the Howard's algorithm, and it's also from the 50s actually. So it's an algorithm which is actually really old. Okay, yeah. So let me maybe, so at this point it's maybe a good point to mention also the contribution of other people. And it's a long list. I mean, I've here put 2 slides here. And you can see that, I mean, there's a long list of contributions going back into the 80s when this whole viscosity idea also took off. I put here in sort of italic letters a little bit the papers which gave us the most insights. And so there's, of course, Balzerganides. That's clear. I just cited it. And then also, of course, the Obermann-Fröse-Benamou papers follow related ideas, but they stay with the original Monge Ampère formulation. And Then on the Bellman side, I think we learned a lot from these papers by Jacobsen and Ali. So he's certainly not the first person to think about semi-Lagrangian methods for the Bellman equation, but at least I think the paper was very nicely written, so it was very good to make our ideas clear. So this is why I would like to mention it. Of course, here in the audience we have also Brenner and Sung, who also worked on Monge Ampere with DG methods as well. And another paper I should mention is, I didn't put it in italic letters because it's a very new paper. We became aware of it only recently. It's by Christoph Reising and his co-workers, but it follows some very similar ideas as well. So he looks at also semi-Lagrangian schemes for very similar problems, and he thinks about CFL conditions near the boundary to discuss boundary issues. Okay, so now we want to prove convergence, and so I want to focus, I don't want to show you all the technical details, so I want to focus more on the aspects arising near the boundary. So I want to quickly just tell you, we show that we have got uniformly bounded solutions, we have consistency in omega, but we do not have consistency near the boundary. In fact, we do think our method would in some sense be inconsistent in the original notion of Walzer-Ganides, because we truncate, we squeeze our PDE operator near the boundary, and so in the viscosity sense of boundary solutions, we don't have consistency. But we have monotonicity, because that semi-Lagrangian schemes are really good at that. Okay, but focusing now on the mechanics of the Walzer-Ganides proof, and focusing also on the boundary conditions again. So what Walzer-Ganides do is they take the numerical solutions, and then they take what is called taking the semi-continuous envelopes of that. So that's this lim sup operation where you take y to x and simultaneously you refine your computation. That gives you this upper and the lower envelope. And sort of then there's argument, which by now is a standard argument, says that this guy here is a sub-solution and this is a super-solution of the PDE and of the viscosity boundary conditions. Yeah? And then if you have now a comparison principle with viscosity boundary conditions, you actually at this point get an L infinity convergence proof out of it. But the issue is now that, okay, I rewrote down what these viscosity boundary conditions amount to, which is an obstacle problem on the boundary between your operator, this fully nonlinear operator, and the boundary data. Those comparison principles usually do not exist if you've got an anisotropic degenerate equation with Dirichlet boundary conditions. And in fact, I think I can give an indirect argument why you do not have this boundary comparison principle in our setting. The other issue is, even if you had this comparison principle, we still have got this issue of consistency near the boundary because we squeeze our scheme. So two reasons why the original Walzer-Ganides scheme actually proof does not apply here. In fact, a third reason, no, just two reasons, yeah. No, it's just two reasons why Walzer-Ganides does not apply in the original form here. So the issue arises from so what we want to do instead is we want to now show that we have pointwise boundary conditions. We satisfy them also for these envelopes here, because we already have our comparison principle then in that setting. But this is a stronger notion, and in fact the issue arises that a priori you do not know whether your numerical solution builds something up which looks like a boundary layer. And if they build something up like a boundary layer, then they could sort of switch off your Dirichlet operator, violate to satisfy the Dirichlet boundary conditions, and just instead only satisfy the PDE on the boundary point. Yeah, so we have to make sure that this boundary layer cannot arise. And so the question is there sort of a reason why we might get away with this? So I think we have to sort of revisit conceptually what Vazov-Motzkin is really trying to tell us, and see to understand what might go wrong. Now, what Vazov-Motzkin is saying is that if you squeeze your stencil too much, there exists a test function for which you do not have consistency. But the thing is, so then the question arises, so okay, but maybe I save some of the test functions. So maybe there's still some test functions for which I keep my consistency. If I keep my consistency for some test functions, they might give me enough control on what happens in the boundary. Because, of course, what happens in the boundary becomes a smaller and smaller and smaller sausage. So the sausage, maybe it's very small, it's enough if I sort of can sort of in a rough way control it. Now, the thing is, Vazov-Motzkin tends to fail if you have got test functions which are very anisotropic themselves. But when you've got isotropic test function, in fact, if you take a test function which looks like this, yeah, so totally isotropic, the contour lines are really perfect circles, and I would now be given a PDE operator. A PDE operator would be like a black box. I don't know which operator is inside, and I can only test with my circular test function. I could not tell you whether the PDE you have given me in the black box is an anisotropic PDE or is an isotropic PDE. So somehow, since I can't tell it, also the consistency cannot be broken. Yeah, I mean, if you so what I wanted to sort of motivate is that all the test functions more or less look isotropic. They stay consistent. And now I have to just work with these test functions to show that this boundary layer cannot build up. Yeah? So in fact, it's already enough to work with these perfectly isotropic test functions. And if you do that, so you have got this construction here, moving here your point M and your point P and so on, and you control the boundary layer doesn't go up. So it's a terrible, I'm not going to tell you this because it's just very technical, but in fact, there's an interesting point which goes back actually to what Carsten said. Where does convexity go into our analysis? And as far as our numerical analysis goes, and the only point where we use convexity of the domain is actually when we want to show the existence of suitable test functions to show that the boundary layer doesn't blow up, get created. So if you say Barnes-Organides is a proof of well-postness, and then do need to bring in convexity at some point, the only point where convexity arises in our analysis is when we go and choose our boundary conditions. So that somehow also says that if you could do it with the viscosity boundary conditions, you could actually prove well-postness without any convexity constraints, and that's against sort of the common knowledge. So that seems to be an essential point. Okay, and then once we have that, we basically modify our Barnes-Organides framework, and we get the convergence, uniform convergence to the viscosity solution of the Bellman problem / Monge-Ampère problem, since it's the same function. Okay, so summarizing that, we have this well-posed problem. We have a globally convergent solver, we have uniform convergence, and convexity only enters through the choice of the boundary conditions. Okay, then numerical experiments. I just want to show you two things. I mean, once we want to look at a smooth case, so that's here, this is this quadratic function, very smooth. It's a classical solution. And one, this kind of modulus-like function, so that's a viscosity solution. It's not a classical solution. And so this is here how a convergence picture looks. A bit weird. So how does this come? Because we have now two things to think about. We have to think about our mesh size h, and we have to also think about our stencil size k, because these are now two different things we fix. And what we did now here, to somehow picture this better, we said we have a multiplier m, and we say k is m times h, and then for a fixed m, you see here, this is sort of one of those lines here. So the blue line, for example, this one here says, my stencil is twice the size of my mesh. Yeah, and you see that at this point, at some point, I refine more. I don't improve my convergence anymore. This is because of the artificial diffusion, which doesn't go away if I don't change my m. Yeah. So if I refine, as I refine, I slowly have to increase here my multiplier, have larger and larger stencils related to the mesh size. And this is sort of roughly a square root relationship here for the smooth problem. And you see that I start here with about 90 degrees of freedom here, and here I've got, I think, 1.2 million degrees of freedom, and you can see here how this convergence proceeds. And in the non-smooth problem, convergence is not as fast. So you see this is here actually the same axis, the same scale. So here to better than 10 to the minus 3 in the L infinity norm. Here it's more like closer to 10 to the minus 2, well, a bit less, but it's slower, and I also have to make my stencil larger at a faster speed. That's something we don't actually fully understand yet, but it's the same picture. And then finally, regarding the numerical experiments, we have got this Newton solver, so it's always interesting how robust it is. So you can see this is the picture for the smooth problem, this is here the picture for the non-smooth problem, and we have here in the box is always the optimal choice, so always the node which gives you here the minimal error on a given mesh. And that's, of course, what you're aiming for. So you have about 5 iterations on the coarses mesh, and you go, after 7 iterations, you go to 8 or 9 Newton iterations. And this is just picking some starting point, so it's not fine-tuned close to the already existing solution. And I think that is reasonable enough. Which brings me to the end of my presentation. So let me just summarize. And I think that there are sort of two messages there fitting to the two parts of the talk. The first one was that really there's this question of translating Monge Ampere to Bellman. Is there something to be gained from it? And in terms of numerical analysis, I think definitely because you have a much better way of posing your uniqueness and convexity, which is more suitable for numerical methods, whichever kind of numerical method you would like to take. And also this allows us to include the degenerate case, which can be with other approaches less straightforward. So sometimes for some approaches you like to assume that here's a lower, they're bound uniformly away from zero. So that's something we do not need to do. And then using that idea as a concrete scheme, we presented this scheme of semi-Lagrangian type, where we showed for that now the convergence to the viscosity solutions. We had a good look at the boundary conditions and thought that the pointwise sense is the right thing to do. We have the Newton method, which always converges. And in fact, I didn't mention any mesh conditions because there aren't really any. So we don't need strict acuteness of the mesh, and it can be an unstructured mesh. Okay, thank you very much.